Testing. Okay, good evening. Good to see you again. Okay, so we will continue from, I guess this is where we stopped. We were on the verge of talking about the concept of frequency domain description of signals, right? So just recap a little bit. So we were talking about, okay, so if you have a periodic signal like this, let's say a triangular wave like this, and then so since this is aperiodic, right? So when we talk about frequency, when we ask what's the, oops, what does that mean? Can I just click here? No. Well, anyway, I don't think the screen is matters too much because most of my elaboration is in the whiteboard. Anyway, okay? You can use a little bit of imagination to imagine what's to extrapolate what's, okay, that's good. What happened? Anyway, so and then we were talking about, okay, what do we mean by frequency of this signal, right? And then we remember from our previous discussions, frequency is defined as number of cycles over 1 second window, right? So, but for this waveform, you look across the waveform, you don't see anything called cycle because there is nothing that repeats itself. So, from the basic definition of frequency is the undefined for this kind of aperiodic signal, right? But then, last time we explained that, okay, this can be decomposed into, I put a double quotation mark here, summation. Is adding up a large number of sinusoidal Legos. Each of these sinusoidal Lego have parameters. There are 3 parameters: amplitude, frequency, and phase, right? So if you decompose this waveform into these basic building blocks, we imagine this is like a house, and then this is like the Legos behind the house. Each of these Lego has a parameter: amplitude, frequency, and phase, right? So we cannot talk about frequency for this guy, it's not defined. But for each of these Lego, can we talk about frequency? Of course, they are periodic, right? So frequency is well defined for each of these single Lego. So then, when we talk about frequency for this aperiodic signal, we are actually talking about the frequencies behind these basic building blocks that compose this original waveform, okay? So now if we have to describe this object called signals, we have 2 choices. The first choice is we talk about this waveform. It's called time domain. Using my Lego analogy, it's like you talk about this assembled house, talk about the feature of this house, like this waveform is a triangle, right? Or like this house has 4 windows and whatever, okay? So that is the time domain description. But then we have a second choice. The second choice is we can dismantle the house. We don't talk about the house as a whole. We dismantle the house into many pieces of Legos, and then we talk about what composes of the house, right? What are the parameters of these individual Lego pieces? If we do this, this is called frequency domain description. Is that okay? So frequency domain description is nothing but just giving you the parameters behind all these Legos, the parameters of the Legos behind this waveform, okay? So, and of course, sometimes just giving you a long list of these Lego parameters is not that user-friendly. And sometimes we would like to use graphical methods, right? So there are usually 2 graphs. One is called amplitude spectrum. Amplitude spectrum. That is listing all the amplitude and frequency relationship of the Lego components. For example, the first piece of Lego has a frequency of F1, amplitude A1. Second piece, frequency F2, amplitude A2, etc. We form a spectrum like this. So this is just a graphical description of these Lego parameters, okay? If you have difficulty of understanding this graph, you can always go back conceptually, go back to this list. Is that okay? All right, so this is amplitude spectrum, but of course we have phase spectrum as well. So this is called phase spectrum. So like you take the first piece of Lego, look at the frequency f1, and then the phase is theta 1. Take the second piece of Lego, frequency f2, phase theta 2, etc. Okay, so that's the phase spectrum. So we can all understand this, right? So when we talk about frequency domain description, it's talking about the parameters behind the basic building blocks, which can be represented graphically using these two graphs, amplitude spectrum and phase spectrum. And I guess last time we also mentioned, so like for this case, right, we have a wheel signal waveform like this, but then, so when we represent this frequency domain description using the amplitude spectrum and phase spectrum, we only see one-sided spectrum, right? We only see positive frequencies. Now, for this convention, one-sided spectrum, positive frequencies, that means our basic building blocks, this Lego, is defined to be an cosine 2 pi fn plus theta n. This is the wheel sinusoidal, okay? Because the Lego is of this form, so this frequency can only take positive frequencies, right? Non-negative frequencies. Is that okay? Because so this representation requires positive frequencies. However, there is a second type of Legos that we can use. I call this tilde. This second type of Lego is a compressed sinusoidal. So this is a compressed amplitude, which embraces both the phase and amplitude. And then you have EJ2 pi Fn t. So this is the compressed sinusoidal. Okay. Now this piece of Lego is related to this original wheel piece of Lego according to this formula, right? So this wheel Lego is equal to 1/2 of this compressed Lego plus this compressed Lego conjugate. Is that okay? So then you visualize this as one piece of compressed sinusoidal Lego with positive frequency, and then this conjugate is another piece of compressed sinusoidal Lego at negative frequencies. Is that okay? So now if your box of Lego is of this type 2, then your list of these Legos, right, will cover negative frequencies as well, right? So if you are using this red Lego as your basic building blocks, then your amplitude spectrum and phase spectrum will have the negative frequency components as well. Is that okay? So when you see two-sided spectrum with negative frequencies, now don't panic. It just means that your basic building blocks have this compressed sinusoidal form. Okay? If you see positive frequencies only, it just means that your basic building block is of the blue form. Both are equivalent. Is that okay? All right. Now, so as I illustrate last time, I guess, right? So if you look at this example, so this is itself a sinusoidal signal, right? So if you decompose this into the basic building blocks, the Lego, this will only, it is a Lego by itself. So you only see one piece of Lego at frequency 5 kHz, amplitude 1 volt, right? Now if you look at the second example, this waveform is slightly more complicated. If you dismantle this, decompose this into the Legos, you see that this guy consists of two Legos. The first sinusoidal Lego has frequency 5 kHz, amplitude 1 volt, phase 0. Is that okay? And the second piece of Lego has frequency 10 kHz, amplitude 1 volt, and phase 0. Okay? In the third example, it's even more complicated waveform. If you dismantle this into the basic building blocks, you find that this guy consists of three pieces of Legos. First piece at 5 kHz, amplitude 1 volt. Second piece, 10 kHz, frequency 1 volt. Third piece, frequency 20 kHz, amplitude 1 volt. Is that okay? In this final example, rectangular wave, if you dismantle this into the basic building blocks, now you see you have an infinite number of sinusoidal Legos. Okay? First piece at 5 kHz, amplitude 4 over pi, second piece, etc. Okay? You have infinite number of Legos. Is that okay? In all these examples, we only see one-sided spectrum, right? So that means the Legos behind this representation is the wheel Legos, is the wheel sinusoidal, the blue one. Okay? If you start seeing negative frequency components as well, that means we are then for the two-sided spectrum, that the basic building blocks we are using will be the red Lego, compressed sinusoidal. And of course, as I said, because of this, both are equivalent. Okay? That means if you give me this blue Lego, I can further dismantle this into 2 pieces of these red Legos. Is that okay? All right. Now this is another visualization. So if I have an object called signals that I want to represent, I have 2 choices. The first one is I talk about the features of the waveform, like the red color. Okay, so this is the time domain description. A second choice is, okay, I don't talk about the feature of the waveform. I try to dismantle this into a number of sinusoidal Legos. Those are represented by the blue waveforms. So this blue sinusoidal is the first piece of Lego, represented by frequency at this location and amplitude with this location, with this amplitude. The second piece of Lego is like this. That is represented by the frequency component at this position, at this frequency and this amplitude, etc. Okay? So the second choice is I don't talk about the waveform anymore. I just talk about what are the Legos behind this waveform. Okay? So these are the 2 choices of description of signal at this point. All right? Time domain, frequency domain. All right? Now, I put a quotation mark here as a summation because this is technically incorrect. What do I mean by this? In general, if this is an aperiodic signal, when you try to dismantle this into Legos, of course we know we have infinite number of Legos, right? But it's more than infinite. When we want to sum, when we put a summation here, we are implicitly assuming we are doing a countable sum. We are summing up countably infinite number of Legos, okay? But in many circumstances, especially in the aperiodic case, the number of Legos is uncountably infinite, okay? So if we want to add up uncountably infinite many sinusoidal components, we should not use summation. What should we do? We should do integration, okay? So for those of you who have studied Fourier transform before in your undergraduate, you should recognize this formula. This formula is called the analysis equation. If you look at this equation, the time domain waveform is given by integration of this right-hand side, right? So what is integration? Conceptually, it's nothing but just a summation. But this integration is doing just uncountable sum. So what do you sum up? You sum up this integrand. What is this integrand? Consists of a compressed envelope multiplied by a compressed sinusoidal. So it is integrand that you are adding, you are summing over is this compressed sinusoidal. Okay? So what you are doing is you add up. When I say add, you are doing uncountable addition. Okay? You add up all these compressed sinusoidal components. The frequency component will cover from negative infinity to positive infinity. Okay? So you see that under this convention, we are using these compressed sinusoidal basic building blocks. So the addition, the range of frequencies that you add over cover the negative frequencies as well. Is that okay? So now when you read this formula, you should not be panicked. This is just the same, conceptually the same as this. Is that okay? Except that we just make it mathematically rigorous because we are doing uncountable sum. We want to sum up uncountably infinite number of components. So we cannot write summation. We have to use integration. Is that okay? Now this compressed amplitude embraces both the real amplitude and the real phase. Is that okay? So if you express this compressed number into polar form, you will get back the amplitude and the phase. All right, so this equation gives you what? If I give you the list of the sinusoidal Legos, you can use this formula to assemble back the waveform, to assemble back the entire house. Is that okay? Now, the other equation that you may have learned before is called the transform equation. So this transform equation is the other way. You give me the waveform. I use this formula to compute the compressed amplitude of the sinusoidal components. Okay? So this is giving me the compressed amplitude of the F compressed sinusoidal components. Okay? So you use this formula to do the transform. That is, I give you the time domain waveform. You use this transform equation to figure out what are the sinusoidal components. Okay? And then the other way, if I give you this the list of sinusoidal components, you use this formula, the left-hand side formula, to assemble the original time domain waveform. Is that okay? So therefore, they are one-to-one correspondence. Now at this point, we should understand time domain and frequency domain description are just two sides, two angles to look at the same object called signal. Okay? The physical properties of the signal will not be changed, will not depend on which angle you look at that. What do I mean? For example, physical properties include energy. The energy of the signal can be computed from time domain, like this formula right-hand side is the time domain equation to compute energy, or frequency domain. The left-hand side is the frequency domain method to compute the energy. Both are the same. Okay? If you study Fourier transform, this is called Parseval theorem. Okay? Can be proven mathematically. Is that okay? So now you can compute energy from time domain, you can compute energy from frequency domain, they will give you the same answer. Okay? So keep this concept in mind. Using time domain or frequency domain is just looking at the same physical situation from different angles only. What happens behind the scene, the physics behind the communication or signal processing, the physics behind this remains to be the same. Okay? Now, this formula also give us an idea. Now, we say that, okay, conceptually, we still use the conceptual summation, okay? Give you a certain time domain waveform, you can decompose this into many sinusoidal Legos, right? But not all sinusoidal components are equally important, okay? So why do I say that? Those sinusoidal components with larger amplitude would be more important. Why is that? You look at this equation. This equation, what does that tell you? Integration means a summation, right? What do you sum over? You sum over the amplitude square of a sinusoidal component. When you sum them up, you give you the total energy, right? So that means if I have a sinusoidal component which have very small amplitude, that sinusoidal component, if I throw this away, is going to account for very small distortion in energy sense, right? You only lost a tiny portion of the energy, right? If I throw away a sinusoidal component with very small amplitude. Is that okay? So keep this in mind, the importance of sinusoidal component is reflected by the amplitude, okay, from this formula. With this understanding, so these are some examples, right? So you have, if you have to compute Fourier transform. Now, of course, in this course, I won't test you on how to compute Fourier transform. So if you have never learned about this before, don't panic. This is just for your information, right? So if you have a rectangular pulse like this, on the left-hand side, this is a time domain waveform. If you dismantle this into the sinusoidal building blocks, this is the amplitude spectrum on the right-hand side. So, of course, as I said, it consists of uncountably infinite number of sinusoidal components. This is a two-sided spectrum, so that means the sinusoidal components take this complex sinusoidal form. Okay, so therefore, that's why we have two-sided spectrum. And then this is the amplitude versus frequency of the spectrum. The phase is always zero. Okay, so this is just a graphical description of these parameters behind this uncountably infinite number of Legos. Is that okay? So with this understanding, there is a concept called bandwidth. Okay, now let's revisit the concept of bandwidth. What do we mean by bandwidth? As I just mentioned, right, not all sinusoidal components are equally important, right? Some are more important than the others. So what do we mean by bandwidth? Bandwidth is a window of frequencies, like this is the amplitude versus frequency, amplitude spectrum. So bandwidth is the window of frequencies. Within this window, all the sinusoidal components within this window are very important components. Right? If you throw them away, you're going to suffer from a big loss. Okay? Those sinusoidal components outside this bandwidth window are less important sinusoidal components. If you throw them away, it's going to contribute very small loss in energy. Is that okay? So, for example, let's say we take a convention of 99% bandwidth. That means if this is a 99% bandwidth, that means if I throw away the sinusoidal components outside this window, I throw away all these sinusoidal components outside this bandwidth window, I'm only going to lose 1% of the total energy. Is that okay? And that's called 99% bandwidth. Now, so bandwidth, conceptually, is a number that gives you the range of frequencies containing important sinusoidal components. Importance in energy sense. Okay? Now, however, there are different conventions. One convention is, as I just talked about, in terms of 99% percentile. Okay, so that means if this is, if we say that the 99% bandwidth for this signal is 1 megahertz. That means outside this 1 megahertz window, you throw away all these sinusoidal components. Outside this 1 megahertz window, you are going to lose only 1% of the energy. That's the so-called 99% bandwidth. That's one convention. Second convention is sometimes people refer to 3 dB bandwidth. That means, let's say the largest sinusoidal component's amplitude is normalized to 1 unit. Then you look at the range of frequency components where the amplitude dropped to 1/2. 1/2 means 3 dB. This window is the 3 dB bandwidth. Is that okay? That's the second convention. These two conventions may not have to be equal. Okay? The third convention is the first zero crossing point. For example, if this is an amplitude spectrum, okay? Somebody defined the bandwidth of this waveform as the first zero crossing point across this. So that would be the bandwidth for this rectangular wave using zero crossing convention. Okay? So if I have to ask you to compute the bandwidth of a signal, I have to tell you what convention I'm referring to. Okay? So without that, there is ambiguity behind the bandwidth. But I guess you don't need to worry about the differences between this convention. The important thing is the concept behind bandwidth. Those frequency components within the bandwidth window are important frequency components. Is that okay? That's the most important concept. Okay? So a signal with larger bandwidth, what does that mean? That means this signal, if you try to decompose this into sinusoidal components, this signal with large bandwidth means you have you have more important sinusoidal lagos, okay, compared to signals with smaller bandwidth. Okay? Now, without doing the tedious computation, there are something you can rely on for qualitative comparison of the bandwidth between signals. There are two factors that will affect bandwidth. The first factor is called pulse shape. If you look at the time domain window, how does the waveform look like? Now, these are two examples. On this side, this is a rectangular pulse. If you look across this waveform, you will see the waveform has a sharp jump. It's discontinuity here and the discontinuity here. Okay? So if you look across the waveform, you see this kind of discontinuity. If you then decompose into the sinusoidal lagos, you will see that pulses with sharp transitions will generate a large number of significant higher frequency sinusoidal components, as you can see here. So you have a long tail in the sinusoidal components. This is amplitude versus frequency. Okay? So on the other hand, for the waveform, for the waveform in the right-hand side, it's a smooth pulse. You look across the waveform, this is time, this is the voltage. Look across this waveform, you don't see any discontinuity. You see the waveform is very smooth. Okay? Now, if you can dismantle this into the sinusoidal basic building blocks, look at the amplitude spectrum, you see that for this waveform, the amplitude spectrum are concentrated within this small window of frequencies. Okay? So if you compare these two, that demonstrates the first idea. Sharp pulses will result in higher bandwidth like this. Okay? So if we take the convention of 99% bandwidth, for this first signal, the bandwidth may be this window. Okay? You have to include these components as well. But for the second example, the bandwidth is just within this small window. Is that okay? So that's the first factor. If you look at the pulse, the waveform features, whenever you see discontinuity, sharp jump, sharp transition, these will generate higher sinusoidal components, higher frequency sinusoidal components. All right? The second factor is the pulse duration. So what do we mean? So for example, if you focus only on smooth pulse, if I have one pulse like this pulse duration is 1 unit. I have another pulse which is compressing the time axis into 0.5 unit. The second pulse will have a higher bandwidth than the first pulse. Okay? The reason is because for Fourier transform, again, this can be mathematically proven. The pulse duration in time domain times the bandwidth in frequency domain, these two parameters multiplied together is larger than or equal to a constant. Okay? So this is coming from the definition of Fourier transform. It can be proven mathematically. But the interpretation of this is very important. That means if I compress the time domain waveform, I squeeze the pulse duration. I squeeze this into half. Okay? Then the corresponding bandwidth needs to be doubled. Is that okay? And vice versa. If I squeeze the bandwidth into half, then the pulse duration will be doubled. In other words, I cannot simultaneously reduce the pulse duration and reduce the bandwidth. Okay? This is, if you recall from your good old days, high school physics, you heard about uncertainty principle, right, in quantum mechanics. The uncertainty principle is actually coming exactly from the same relationship. Okay? It's based on the Fourier transform properties as well. So this is the basis for uncertainty principle in quantum mechanics as well. Okay? In quantum mechanics, you get used to this delta x times delta p larger than or equal to some constant. Right? So that means you cannot simultaneously have a precise knowledge on the location and the momentum. Right? So that is the same idea here. All right, so therefore, if you have the same pulse shape but you compress the time axis into 1/2, then the bandwidth will be doubled, and vice versa. Is that okay? Now, based on these two properties, sometimes you can compare the bandwidth of different waveform using these two principles without going through the Fourier transform computation. All right? So here, the important message is, what do we mean by bandwidth? At this point, we should know what do we mean by bandwidth, right? We introduced the concept of bandwidth last time when we introduced the Hkust sampling theorem. When we do the so when we do the sampling, we say that the sampling process can be reversible if you sample sufficiently fast, right? How fast is sufficiently fast? If you sample at a rate larger than 2 times the bandwidth, then the sampling process will be reversible, right? So at that time, I just say we pretend we know what is bandwidth, but now we don't need to pretend. We should know what it means by bandwidth, okay? A waveform having a larger bandwidth, that means if you dismantle this into the sinusoidal components, you will see that that signal will have more important, will have more sinusoidal levels of great importance, okay? Put it this way. All right, so now, so far we talk about how, right? How to convert from time domain to the frequency domain, and what do we mean by that, okay? Now the next question we want to explore is why. Why do we want to do this? Now, so it's so troublesome, right? So if we can describe the signal using the waveform, it's very intuitive, right? Easy to understand. But when we talk about frequency domain description, it's so troublesome, so abstract, right? We have to interpret the frequency domain description not in a very intuitive way, right? So, but then why? Why we want to go through the trouble to represent signals using another domain? Okay, so there are many reasons for that. First, efficient storage of signal, compression. So last time when we talked about analog to digital conversion, right, digital music or digital video, we said that if you just convert video into digital format using the brute force approach, sampling and quantization, the problem is a 1-hour movie may require 10 CD media, right? So it's totally impractical. So the missing piece for digital video is we need to find an efficient video compression engine, so-called MPEG-1, to do the compression, right? So why on earth can we compress information to start with? Now, if we only know about time domain description, so if I have a piece of waveform, let's say a piece of music, right, with a duration t. So we think about storing this piece of music digitally, okay? So how do we store it? Well, using Hkust sampling theorem, we say that, okay, we don't need to store the entire waveform. We just need to keep the samples. We just need to store the samples, because if you sample more than 2 times the bandwidth, then this sampling process will be reversible, right? If you find some ways to store the values of these samples, when you play back the values, right? And then you use the D to A conversion process, you will get back the original waveform, right? So from a storage perspective, I just need to worry about how do I store the values of these samples, right? How many samples do I have? The sampling frequency is 2 times the message bandwidth. That's the minimum requirement, right? And then total number of samples over this duration is, so total number of samples equals to 2 times, this is the sampling rate, times the duration, okay? 2WT. So that means I just need to worry about how to store 2WT number of samples, 2WT values. If you look at each of them as a, I don't know, fixed point number, let's say 8 bits per values, then is this number 2WT bytes of information. Is that okay? Now, so with this understanding, is there any opportunity for compression? When we talk about compression, that means we have to throw away some less important samples and keep some more important samples, right? If you look at this time domain, if time domain is the only way you can describe the signal, all the samples are equally important, right? You cannot say this sample is more important than the others. Is that okay? And because of that, there is no space for compression at all. However, and by the way, for some of you who have studied, I don't know, signal processing, information theory, this number should not be, you should be familiar with this number. This is called the basic degrees of freedom behind a waveform. Okay? But if you don't know what I'm talking about, never mind. Okay, so now if we know, by now we know there is a different way to represent signals, right? So if we try the frequency domain description, we look at the sinusoidal components, right? The amplitude. Then maybe after we dismantle this guy into the basic building blocks, into sinusoidal Legos, right? We may have the Legos like this. Let's say like this, okay? So what does that tell us? Now, of course, strictly speaking, if I don't allow any loss of fidelity, right, then I need to worry about how to store the values, how to store the parameters of these 5 pieces of Legos, right? Let's say this guy dismantled into 5 Legos only, okay? And then these are the amplitude of these 5 Legos. If I'm talking about total 100% fidelity, then of course I need to worry about how to store the parameters of these 5 Legos, right? But now, if we allow a little bit of loss of fidelity, just like MPEG-1 or MPEG-3, those are lossy compression, right? That means there is a loss. But we control the loss to a very small number. If we allow some loss, then what should be the strategy? We should focus our effort to worry about how to store the parameters of these 2 important Legos, right? And we can forget about the other 3. Why? What are the bases for this? Because as I said, not all these Legos are equally important, right? Some are more important than the others. How do we know which one are more important? Look at the amplitude. What are the bases, theoretical bases for ranking the importance of sinusoidal components according to amplitude? What are the theoretical bases? This is the theoretical basis. Is that okay? So because of that, for the same problem, when we talk about storage of signal, when we look at this same problem from a frequency domain angle, we suddenly see opportunity for compressions. Okay, so that's one example. And that is exactly what these MPEG-1, MPEG-2 are trying to do. Okay, they try to express the waveform in another domain. And in another domain, they can, very often, there are more important components than the others. Okay, then you can focus your energy, focus on your storage budget to store these pieces of parameters and ignore the others. Okay, or may not be completely ignored, but use a less storage budget for the other less important components. Is that okay? There are many variations. Okay, so that's the first motivation why we want to represent information from another domain, although that other domain, the frequency domain, seems to be more abstract. Okay, from a storage perspective. Second motivation, sometimes when you do signal processing, okay, when you do signal processing, you will be able to develop intuition, a better intuition from another domain, from frequency domain. Now, just use this Nyquist sampling theorem as an example. We say that if you sample sufficiently fast, the sampling process will be reversible, right? But if you look at the time domain, like this, it is very difficult for you to understand why this is the case, right? Because if you look at how much information have you thrown away, you have actually thrown away many information in between the samples, right? In fact, technically speaking, you have thrown away uncountably infinite number of information in between the samples. So how could this be reversible, right? Now, but if you look at the same process from sampling process from a frequency domain angle, then it will reveal some very easy insight, intuitions. Now, what I mean is, let's say this is the original waveform in the analog domain. Time domain description, and now if you dismantle this into the Legos, this is the frequency domain description. So this lists the parameters of the sinusoidal Legos behind this waveform. Is that okay? Those are one-to-one correspondence. Okay. Now in the time domain, what do we mean by sampling? To understand sampling, we introduce a periodic impulses like this. So this is a periodic impulses. Now for those of you who have studied Fourier transform before, you should know that the Fourier transform, if you dismantle this periodic impulses into the sinusoidal components, the frequency spectrum is also given by periodic impulses like this. Okay. Now this can be shown mathematically. Now, so what do we mean by sampling? Sampling in the time domain is simply take the original waveform, multiply with these periodic impulses. Why? Because after you multiply the periodic impulses, the time domain waveform becomes something like this. Because impulses, what do we mean by impulse? Impulse gives you a singularity only at the support level. In between these impulses, you have zero, right? So after this multiplication, what you get is only at the singular level, right? Those values in between become zeroed. This is the mathematical meaning, the mathematical expression that model the sampling process. Okay. So this is what happened after sampling in time domain. So as I said, if you just look at this time domain sampled waveform, it's very difficult for you to see any intuition why this can be reversible, right? But now we understand if we look at this waveform, this sample signal from a frequency domain perspective, that means you're trying to compute the Fourier transform of this sample waveform. This is the same as computing Fourier transform of this multiplication. Now, after some algebra, which I'm not going to elaborate, this Fourier transform can be expressed in terms of these results. Okay, where G omega is the original amplitude spectrum. Okay, so the spectrum of this sample waveform is equal to the summation, infinite summation of these components, right? What is this? Let's say we take n equal to 0. N equal to 0 gives you this piece. Okay, G omega. What about n equal to 1? The term corresponds to n equal to 1 is G omega minus omega s. This should be omega s, okay? Which is what? Which is this piece. Okay, so if I have to draw it, this is the Fourier transform of the sample waveform. So this piece corresponds to n equal to 0 in the expression. This piece, the center is at omega s. This piece corresponds to n equal to 1. And then you have a n equal to 2, etc. And then this piece corresponds to n equal to minus 1, so on and so forth. Is that okay? So that is the spectrum of the sample waveform. Now, when we say we want to reverse it, what is our objective? If we want to reverse it, that means we want to reproduce the original signal, GT, right? In the frequency domain, that means we want to reproduce this spectrum. Is that okay? So, if I give you this, how can you reproduce the spectrum? How can you reproduce this original spectrum? Very easy, right? You do a simple low-pass filtering. You can do something like this, right? After you do this low-pass filtering, you get back this spectrum. If you get back this spectrum in frequency domain, then that is the same as saying you get back the original waveform in time domain. Is that okay? Now, here there is a condition. For this to work, there must be a non-zero gap here, right? This is 0. So this width is omega s, sampling frequency. This is the bandwidth. So this width is the bandwidth. This width is also the bandwidth. Is that okay? So when we say you sample sufficiently fast, that means this is larger than 2 times the message bandwidth. So now you can see why 2 times, right? Because when this condition holds, that means this total separation is larger than 2 times of the width. That means there are some gaps here. If there's some gaps here, that means this one and this one will not overlap. And that's why you can recover this piece by filtering. Okay? On the other hand, if you do not satisfy this condition, then what happens? It will be something like this. Right? When you have something like this, this piece and this piece will overlap. When you overlap, you cannot regenerate the original beautiful spectrum by just filtering, right? Because this overlap, once you add up this, once you mix up these components, it can never be separated again. Is that okay? So from this, if you look at this whole process, sampling process from a frequency domain angle, this condition becomes trivial. Is that okay? Now, just as a remark, I guess last time when we talked about CD, digital music, right? We say that the bandwidth for music is 20 kilohertz. Okay? But the sampling frequency for CD is chosen to be 44.1 kilosample per second, right? This is larger than 2 times the bandwidth. So why not just choose it to be exactly 2 times the bandwidth? At that last time I mentioned this is for implementation convenience. Now you should also see that. If this is exactly equal to 2 times, then what happened? It's like this situation, right? There's 0 gap here. So this guy just touched the image, right? So yes, theoretically speaking, this is still separable. You can still use a low-pass filter. But then you have to use an ideal low-pass filter, what we call a brick wall filter. Now, if you study EE before, you know that brick wall filter is very difficult to realize. If you build analog filter, the filter may easily becomes unstable. If you build digital filter, the numerical computation can easily be numerically unstable as well. Okay? So it's difficult to do it. Now, what happens if you have a larger than 2 times the bandwidth? It would be like this situation. In this situation, to recover the original waveform, you just need to use this filter. It's not a brick wall filter. Okay? So for this kind of filter, it's much more friendly for implementation. Is that okay? So that's why CD use a sampling frequency slightly larger than 2 times for easy filtering. Okay? But anyway, so the theme here is the second motivation is if you are able to do signal processing from another domain, you will be sometimes, this is not guaranteed. I don't mean it's always better to do signal processing in frequency domain. But for some problem, looking at the problem from a frequency domain can reveal some intuition which cannot be obtained in time domain. Is that okay? Third motivation, telecommunication. Okay? So in telecommunication, as we talk about the example of a submarine cable, coaxial cable, to do long-distance communication, right? Remember at that time we say that the coaxial cable will introduce attenuation. Your signal will get weaker and weaker. Also, we have thermal noise at the receiver, right? So if you only know about time domain description, this will be the picture. Your signal, the good term, the waveform will be contaminated with noise, right? And then at the end, your received waveform will be a distorted, contaminated waveform. Is that okay? Now, if you only know about time domain description, obviously, the waveform when you are added with noise can never be separated. Noise can never be separated if you once it starts to contaminate the signal. Is that okay? When you add when the waveform is added with noise, you cannot remove the noise anymore. Is that okay? That's the time domain. If you look at this from time domain, that's the conclusion you will have. Once the noise is added into your waveform, it can never be separated again. That means there is no opportunity for cleaning up the signal once it is contaminated with noise. Is that okay? Now, however, if you look at this whole process, the same physical process of noise contamination from another domain, from frequency domain, you may have a different conclusion. Let's say this is a piece of your waveform, your signal, your speech. When you transform this when you dismantle this into sinusoidal basic building blocks, sinusoidal Legos, you will see that the sinusoidal Legos have frequency pretty much concentrated within this window. Okay? Now, when you contaminate with noise, again, you dismantle the noise into sinusoidal components. You will see that this is called white noise. That means the noise will have infinite number of sinusoidal components, ranging from negative infinity to positive infinity. They have equal amplitude. Okay? So now when you add these two together, the result will be something like this, right? Now, when you have this, now this is a good term. This is a bad term. After the addition, after the contamination, this is the situation. So if you look at this situation, do you see any opportunity of cleaning up the noise, cleaning up the signal? Partially, right? Because the good term and the bad terms occupy different range of frequencies, right? Can you see that? So noise occupies all the range of the frequencies from minus infinity to positive infinity. But the good term, the term that contains the signals, only have this range of frequencies, right? So that means what can you do? Well, there are many things you can do. For example, you can do a simple filtering. If you do a simple filtering, you can get rid of this out-of-band noise, right? This out-of-band noise will be filtered away. Of course, after filtering, you still have to suffer from in-band noise. This in-band noise occupies the same range of frequencies as your good term, so they cannot be separated by just filtering. But at least the out-of-band noise can be eliminated, right? So this illustrates, if you look at this same physics from frequency domain, you get a different conclusion. You can do some kind of cleaning, right? So this is another example why we want to represent information from another domain, right? Sometimes it reveals different opportunities for filtering or for cleaning up the noise. Now this is a simple simulation. We can do simple filtering using this RC filter, very simple first order filter. Okay, so the blue waveform is like this. It's like this top picture. If you only know about time domain, then the received waveform is given by the blue waveform, which is contaminated with the white noise, and then you cannot separate it out anymore, right? If you only know about the time domain, you have to live with this blue waveform. But if you know about frequency domain, you can do some noise filtering here. When you do some noise filtering here, that means you can do some partial separation. After partial separation, you will get the orange waveform. Now the orange waveform is still not ideal because, as I said, you still have some in-band noise which cannot be separated. But if you look at the orange waveform compared to the blue waveform, it's much cleaner, right? So this is just a visualization. Okay, anyway, so of course there are many more other motivations. This is a long list, but at least with these three examples, I hope it will explain why we want to go through all the trouble to represent signal from another domain, which seems to be more abstract. Okay? To summarize, it opened up more opportunities for compression in the storage application. It opened up more intuitions in signal processing. It opened up the opportunity for signal cleaning in the communication as well. Okay? So now we learn two ways to represent signals or information, right? Now, there is a third way, okay? This third way is what we call geometric domain representation. It is actually, you can think of this or understand this from Fourier transform. Now, so this is in fact a generalization of Fourier transform or Fourier representation. In Fourier representation, what do? We take the wave, I erased that picture. I took the waveform, dismantled it. The waveform is like a house. I dismantled this house into many Legos, right? Sinusoidal Legos. So, and then I talk about the parameters behind each Lego. This is the so-called Fourier domain description or frequency domain description, right? As I said that there is a generalization. The generalization is, the question we ask is, why do we have to restrict ourselves to sinusoidal Legos? Now, sinusoidal signal is easy to describe. It's also a basic building blocks. But this is not the only choice of Legos, right? Okay? So the generalization is, what if we stay away from sinusoidal Legos? We can use some other Legos, okay, as the basic building blocks. Then we can also dismantle the waveform into more advanced pieces of Legos, okay? And that is called geometric domain description. In short, the advantage of using sinusoidal Legos is universal. What do I mean by universal? Doesn't matter the waveform I want to describe is triangular, rectangular, or whatever funny shape. I can always use appropriate choice of sinusoidal Legos to build up that waveform. Is that okay? So that is called universal. Doesn't matter whether my house is a 2-story or 3-story high, whatever the features of the house I'm talking about, I can always use the same set of Legos to build a house, to build different houses. So it's universal. That's the advantage of sinusoidal basic building blocks. The disadvantage is efficiency. To build up a waveform, we usually need uncountably infinite number of Legos. So it's not very efficient. Is that okay? Now, if we can redesign the Legos, if we can tailor the Legos to represent a subset of signals, let's say we don't need to represent all different waveforms. We are only interested to represent a certain set of waveforms. Then we can actually design more efficient Legos. Instead of talking about infinite number of Legos, by tailor-making the Legos, we can actually use just a few pieces of Legos to represent this set of signals we want to represent. Is that okay? So that's the motivation for the so-called geometric domain description. All right, so that's the basic background. Now let's look at what do we mean by geometric domain description. Okay. Now, to explain geometric domain, let's do some quick revision on your high school mathematics, vectors. I guess you learn vectors in high school, right? Okay, so let's have a quick revision. So what do we mean by represent? Okay, vectors, we talk about coordinate system, right? A coordinate of a point, right? Suppose I now have let's say the space I'm talking about is this two-dimensional space on this whiteboard. And let's say I have a point. I talk about coordinates of a point, right? Let's say I have a point with coordinate 1 and 2. Is that okay? Now, is this sufficient for you to locate where this point is? If I tell you I have a point with coordinate 1, 2 on a two-dimensional space, is this sufficient for you to locate where this point is on this whiteboard? What other information do you need before you can precisely locate the point? You understand what I'm asking? Now, if you think the information is already sufficient, then tell me where is this point, 1, 2. If you think this is not sufficient, then ask me what else do you need to know before you can locate where is this point, 1, 2. This is not sufficient, right? If I just tell you I have a point on this whiteboard, the coordinate is 1, 2. Obviously, I cannot locate where is the point, right? What else do you need to know? Sorry?
Base point.
Base point. What do you mean by base point? Origin, you mean? No. Okay, thank you. Let's say this is origin. Is this sufficient? Still not sufficient, right? Now, I'll tell you this is origin. You tell me where is 1, 2. What else do you need to know? You need to ask for the axis, right? Where is my x-axis? Where is my y-axis, right? Correct? If I tell you, okay, this is my origin, and then this is my x-axis, I call this I, and then this is my y-axis, I call this j. By the way, this is called the coordinate system. Okay, I need to tell you in physics term, this is called frame of reference. Okay, in mathematics term, this is called basis. I don't know how you call it in Chinese, but this is called basis. Is that okay? I need to tell you the basis or the axis before you can locate the coordinate, before we can even talk about coordinate. Coordinate without a basis is meaningless. Can you understand this? Now, given that this is my coordinate system with these two bases, I and j, like this, then 1, 2 start to make sense, right? Where is 1, 2 in this case? So this is 1 unit on the right, and then 2 units on the j direction. So this is my point. X have coordinate 1 and 2. Is that okay? My coordinate system doesn't need to be orthogonal. This is an orthogonal system. If I like, I can have a very strange coordinate system like this, right? This also works, right? With this non-orthogonal coordinate system, where is 1, 2? Still, 1 unit on the right, 2 units on the other axis. So this is my point, 1, 2. Is that okay? So my first message with this example is saying that before we can talk about coordinate, we need to establish the frame of reference or the basis first. Otherwise, coordinate doesn't make any sense. Is that okay? So therefore, when we say we want to represent signal using geometric domain, that means we want to represent signals using a point, right, on some space. There are 2 steps involved here. The first step is to establish, suppose I want to represent M signals. Okay, I don't want to represent all signals. I just want to represent M signals. So the first step is to establish the basis or the frame of reference that spans the space big enough to contain these M signals that I want to represent. Is that okay? So the first step is like establishing our coordinate system. Okay. After the first step, that means we have established the frame of reference. The second step is to find out the coordinates for each of these signals. Okay. So when we say representing signals using geometric domain, there are 2 steps involved. Just keep this in mind. Okay. We'll go over this in a minute. Okay. Now to explain how we do it in the signals, we also need to review your mathematics in high school. So let's say we have a basis. We have this orthonormal basis. So the space is given by this orthonormal basis. Let's restrict ourselves to 2-dimensional space, right? So I and j are 2 special vectors. They call this basis, right? That define your axis. These ij are not ordinary bases. They are orthonormal bases. Orthonormal means 2 things. Ortho means orthogonal. That means I and j are perpendicular, orthogonal. Right angle, right? Okay. Normal means the norm of I is equal to the norm of j equal to 1. Is that okay? So unit length. So let's say we have a space defined by this ij, which is orthonormal basis. Okay, so this is our I, this is our j. Okay. Now let's say I have a vector. I have a vector here. So imagine this is a high school exam question. Okay, let's say there's a graph paper. And this is I, this is j. And then now in the graph paper, I draw this vector. And I ask you to find out the coordinates of this vector with respect to this ij. How would you do it graphically? Graphically, how would you do it? What is the x-axis? What is the x-coordinate? X-coordinate is given by this measurement, right? What is this? Mathematically, this is doing a projection. You take this vector, you project onto the y-axis. The projected length is the first coordinate, right? So the first coordinate, the geometric meaning is a projection. It's nothing but just a projection. Similarly, what's the second coordinate? Projection onto the j axis, right? So this is your second coordinate. Is that okay? So when we say, okay, this point, vector has a coordinate x1, x2, what do we actually mean is that this vector can be written as x1 times I axis plus x2 times j axis, right? Okay? If you try to think in terms of Lego, that means you only have two types of Legos in your box, okay? This vector, this object you want to represent can be decomposed into these 2 types of Lego. You take x1 pieces of I Lego, added with x2 pieces of j Lego, then that will form your object. Is that okay? Now, this is a geometric explanation of the coordinate. But how do you find out the coordinate algebraically. How do you do projection algebraically? Now I don't have a graph paper. I give you a vector. How do you compute the projection algebraically? Okay, I claim that the first coordinate is actually can be computed from the inner product. You take the vector, the object you want to represent, and then now inner product is a machine that has two inputs. You feed these two vectors into the machine. The machine gives you an output, a real number. That is the inner product, right? Okay, you think of that as a machine. You feed the vectors. This has to be vector. This is vector. You feed two vectors into the machine will produce a number. Of course, this machine has to satisfy a few axioms as well in order to be qualified a dot product. But let's not worry about the complication. So I claim that the algebraic way to compute the projection is simply feed the inner product machine. It has two arguments, right? The first one is the object you want to represent. The second argument is the basis you want to project onto, in this case, I. I claim that this operation will give you the projection. Can you see why? It's very easy. Let's say you compute this guy. You substitute this into here, right? Then what do you have? This is x1 I plus x2 j. Is that okay? You know that inner product is linear, right? Linear means superposition holds. That means you can separate the multiplication and the addition. That becomes x1 plus x2. Is that okay? From here to here, is that okay? Am I too fast? If I'm too fast, then let's do it step by step. First of all, this is a linear operation. It's a linear machine. Linear machine means that this can be, whenever you see addition in the argument, you can separate the addition. So this becomes x1 I plus x2 j I. Is that okay? Linearity. Again, due to linearity, whenever you see a multiplication here, you can take it outside the inner product. So x1, take it outside, becomes I. Similarly, x2 here, multiplication you can take out of this machine. x2 j I. Is that okay? Now, the basis we chose is orthonormal. So this is what? This is the norm of I squared, right? Which is 1. Is that okay? I guess this is blocking you, some of you, right? So is this better? Minimize the surface area. Okay. So this is what? This is norm of I squared, so equal to 1 by definition, right? And what is this? This is equal to 0, right? By orthogonal properties. So at the end, what do we have? We have x1, right? So therefore, doing the algebraic method to do projection on an orthonormal basis is very simple. You just compute an inner product. The first argument into the inner product machine is the object you want to do projection. The second argument is the axis you want to do projection onto. Okay, but you make sure that these axes are orthonormal basis, right? Otherwise, this will not hold. Is that okay? So, once you have the orthonormal basis, finding coordinates is very simple. It's just a bunch of inner product. So the first coordinate is given by this inner product. What about the second coordinate? Let's try again. This machine takes two arguments, right? The first one, what do you feed into? The object you want to do projection, right? In this case, it's the x, right? What about the second argument? J, right? Is the basis you want to project onto. Is J. Is that okay? So once you have established an orthonormal basis, that is the coordinate system in step 1, finding the coordinates would be very simple. It's just these two inner products. Is that okay? That's what you learn actually in high school. Okay? Now, let's try to do the same for signals. You will find that it's actually very similar. Now in high school, what do we mean by vectors? Vectors is just an abstract object, right? It can represent anything. It's very abstract. So now we're just trying to apply this vector to represent signals. The object we are talking about is signals, okay? So now we have a signal, xt. Before we can represent, what we want to do is we want to represent that as with a coordinate. Let's say x1, x2, okay, on some space. But as I said, before coordinate make any sense, the first step we need to do is we need to establish, just like here, we need to establish a space big enough to contain the signal we want to represent, right? So we first, let's say, going through some method, which we will explain later, okay? Let's say there are some magic behind step one. After going through the step one, we can establish a space. The space is given by a span of two bases. Let's say the two bases are denoted by phi1t and phi2t. Are two specially chosen signals, okay? So this phi1t corresponds to I, phi2t corresponds to j, okay? If you ask me what is phi1t, what is phi2t, I will ask you what is I and what is j. It's the same answer. They are just special types of vectors, okay, that form your basis, form your axis. Same here. Our vector equals signals, right? So what is phi1 and phi2t? They are just special types of signals that form your axis. Is that okay? It's the same answer. Okay, so after step one, we define the space with the two bases. And of course, for the same reason, we assume these two bases are chosen carefully so that they are orthonormal. Okay, once again, what do we mean by orthonormal? Orthogonal, mutually orthogonal. Same here. Okay, that means if you take an inner product of phi1t, phi2t, they give you 0. Orthogonal. Normal means the norm of I and norm of j equal to 1, right? So in this case, what is norm? Self-inner product is the norm, right? This is defined to be the norm of phi1t squared has to be 1. And then the self-inner product of phi2t is denoted as the norm of this guy, also equal to 1. Okay? So by carefully choosing your bases so that they are orthonormal, then you will define a two-dimensional space. Okay? Let's say this two-dimensional space will be sufficient to represent the signals we are interested. Okay? So after step one, we have a basis. We form the coordinate system. Then in step two is easy. I give you a signal. I want to find out the coordinate on that space. Okay? As I explained in high school, finding coordinate of a vector is geometrically a projection operation. Okay? Algebraically, how do we compute the projection? Doing this inner product, right? Same here. Here, I want to represent this signal. A signal here is equivalent to a vector there, okay? So I want to represent this object called signal using a coordinate system. Let's say a two-dimensional space. Then how do I figure out the first coordinate? First coordinate geometrically is a projection. Project from this object we want to represent onto the first basis, right? Algebraically, computing the projection is the same principle, same idea. It's given by the inner product of the object I want to represent, which is xt, and then the basis I'm projecting onto is phi1t. Is that okay? This inner product result will give me the first coordinate. Similarly, the second coordinate, algebraically, is an inner product between what? What's the first argument? xt is the object, the signal we want to do projection, right? What about the second argument? The basis I want to project onto is phi 2t. Is that okay? So step 2 is actually, you have learned about this in high school. So you shouldn't be scared of this anymore, I guess. So step 2 is very easy, just a bunch of inner product. Okay? There's only one thing I haven't talked about. This one thing is something you haven't learned before. Is how do you compute the inner product? Now in high school, in the Cartesian coordinate, you know how to compute the inner product, right? But now here in signals, how do we compute the inner product? So here, the inner product, let's say I have two signals, S1 and S2. The inner product is defined to be like this. It's defined to be the integration of a certain pulse duration, S1t times S2t. This is the new thing here, okay? So this is the way we define the inner product for our space. And we will have the freedom, we can have the freedom to design our own inner product, okay? But this is our choice for our purpose, okay? So this is an operation definition. That means this definition allows you to compute the inner product for signals, for waveforms, okay? Once you have this in mind, the other operation is the same, exactly the same as what you did in high school. Is that okay? So that's why if you look at the second step is, okay, if I have a signal, the ith signal, I want to represent using a coordinates representation. For the ith signal, the jth coordinate is given by this, right? So when you look at that, it looks scary, but in fact, this is nothing but just the inner product of SIT and phi jt. Is that okay? So this is nothing but just computing the projection of the ith signal onto the jth basis. Okay? So second step is easy. The most important part and the difficult part is the first step. How do you find a coordinate system that is big enough to contain, to represent all the signals you want to represent? For example, if I just want to represent these M signals in a certain set, how should I construct the basis or coordinate system? Okay? Now to illustrate this, now of course there is a systematic way for doing this. Perhaps you learned this not in high school, but in your undergraduate. If you have studied linear algebra, I don't know how this is called in mainland, but something related to linear algebra. Do you remember you have studied something called GSO procedure? No idea? Okay, it's the same. You can use the GSO procedure to find the basis. But I will come back to this later. Okay, but let me use a toy example to explain how we find step 1. How do we find the coordinate system, first of all? Let's consider this toy example. Okay, let's say the problem we have is I'm only interested in these 4 signals, x1t, x2t, x3t, x4t. Okay, I'm only interested in representing these 4 signals for some reason. Okay, so what I'm trying to do, in fact, you can think of this coordinate system, the first basis, second basis, as the tailor-made, custom-made Legos. I said that, well, if you want to represent these 4 signals, like this, you can always use Fourier basis, right? You can always use sinusoidal basis or sinusoidal Legos, right? But because sinusoidal Lego you can use because sinusoidal Legos are universal. Okay, doesn't matter what's the waveform you want to represent. Sinusoidal Legos can always be used, right? That's the good thing about sinusoidal Legos. The bad thing about sinusoidal Lego is it's not efficient. Usually it involves infinite number of Legos, right? So now we care about efficiency. And since I'm not concerned about universal representation, I just want to represent these 4 guys. So I want to construct or I want to custom make some Legos, some basic building blocks, which can be used efficiently to represent these 4 guys. Is that okay? That's the intuition behind the basis. Now, okay, so let's try to do it visually. Let's try to do visual inspection. Now, so the first step is to figure out the basis, right? The fundamental basic building blocks, the basic Legos. So what do we mean by the basis? If we can represent each of these signals using a basis, using this phi 1t, phi 2t, that means each of these xt can be written as a linear combination of this basis, right? If we take a certain piece of type 1 Lego, add it with a certain piece of type 2 Lego, I can assemble x1t, x2t, x3t, x4t, right? Using different combinations of these basic Legos, right? If we can do that, then these will be the candidates for the basis for the coordinate system. Is that okay? So now let's reverse the process to think about what kind of basic building blocks can we construct that will be a common basic building blocks behind these 4 waveforms. So then we look at the waveform features, right? These 4 guys are rectangular pulses of different duration, right? Okay? So what if we partition the time axis into 3 time slots? Okay? So we construct the first Lego occupying the first time slot, the second Lego occupying the second time slot, the third Lego occupying the third time slot. We can do this, right? Now if we design the Legos, the basis like this, then we want to check, can each of these x1t, x2t, x3t, x4t be separately decomposed into a weighted combination of these 3 guys? If we can, then this will be good basis, right? If we cannot, then these are not sufficient. Is that okay? So let's try. Conceptually, let's try this. Now, the first basis, the first type of Lego is basically representing the first time slot. The second type of Lego is representing the second time slot. The third type of Lego is representing the third time slot, right? Okay? Now, let's look at x1t. x1t, from this waveform, what would be, how can this be represented by these 3 combinations? Yes, right? x1t would be given by something times phi 1t plus 0 times phi 2t plus 0 times phi 3t, right? Okay? So that means if I have to use these 3 bases as my coordinate system, the coordinate for x1t would be something 0, 0. Is that okay? Let's not worry about that something for the moment. Now, what about x2t? Can x2t be expressed as a weighted combination of these 3 types of Legos? Yes, right? Because x2t, look at the waveform. It just occupies the first 2 time slots, right? So it would be something times phi 1t plus something times phi 2t plus 0 times phi 3t. Can you see that? So x2t is okay, right? So we can also, from this visual inspection, we can also guess the coordinate for x2t would be something, something, 0, right? Now let's go on. What about x3t? Can x3t be represented as a weighted combination of these 3 types of Legos? Yes, right? It will be given by 0 times phi 1t plus something times phi 2t plus something times phi 3t, right? So the coordinate, if we have to use this basis, will be 0, something, something, right? Now finally, what about x4t? Yes as well, right? x4t will be equal to something times phi 1t plus something times phi 2t plus something times phi 3t. So the coordinate, if we were to use this basis, would be something, something, something. Is that okay? So yes, by this simple visual inspection, these are 3 types of Legos, 3 types of common basic building blocks that can be used to represent these 4 signals. Okay? Now they are not universal, because if you ask me if you use this guy to represent triangular waveform, it cannot be used, right? So it's not universal set of Legos. But as long as we restrict our attention to these 4 signals, then these Legos are good enough, right? And they are very efficient because each of these signals only requires 3 types of Legos, right? Unlike sinusoidal Legos, which involve infinite number of pieces. So that's what we mean by efficient basis. Is that okay? So this is, in this example, it's very simple. So we can use visual inspection to figure out what are the bases, right? But this is just a conceptual argument. But this is not the end, right? At the end, remember, we want the basis to be orthonormal, right? We need to check for this condition. So are they orthonormal? So first of all, check about orthogonal. Are they orthogonal? Well, we can just do a computation. We compute the inner product between phi 1t and phi 2t, right? How do we compute the inner product? It's given by this integration, right? You take phi 1t. Phi 1t only have values in the first time slot. This will be multiplied into 0, right? And for phi 2t, only have value on the second time slot. This will be multiplied into 0 here. So at the end, this integrand will be uniformly 0. So the inner product result will be 0, meaning that phi 1t and phi 2t are orthogonal. Similarly, you compute phi 1t and phi 3t inner product, again, will be 0. Phi 2t and phi 3t also will be 0. Okay, so this is very nice. By this visual inspection, we figure out they are orthogonal. The second condition is, are they normal? Okay, well, let me erase this. They in general will not be normal, right? But we can make it normal very easily. Let's take phi 1t as an example. Phi 1t will represent the first time slot, right? So let's say it takes a certain value, alpha. So alpha is a free parameter. It's a normalization constant. We can have a freedom to choose alpha so that it has unit norm. Is that okay? So we want that to be unit norm. We want that to be equal to 1, right? So let's figure out this. This is the inner product of itself, right? By definition, this is integration of what? Alpha square. Well, okay. So this is the integration of phi 1 square t dt, right? And then the integration will only have value in the first time slot. So it will be t over 3 times alpha square. Is that okay? So remember, alpha is the freedom. We have the freedom to choose what is the alpha. So how should we choose alpha? We want this to be equal to 1, right? So that means alpha is chosen to be square root 3 over t. Is that okay? So if we look at the looks here, you see this level to be square root 3 over t, this funny number. So this number is designed as a normalization constant to make sure they are normal. They are normal. Is that okay? So same argument for phi 2t and phi 3t. Is that okay? By choosing this level to be this particular value, we make sure that the norm of each of these bases will be 1 as well. So they are truly orthonormal. Why do we need to make sure, why do we need to be obsessed with orthonormal bases? What's the big deal if they are not orthonormal? If they are not orthonormal, this equation will not hold. The algebraic way to compute the projection will be more complicated. Is that okay? So that's the reason we are usually obsessed with orthonormal coordinate system. Is that okay? So now after we have these bases defined, then we need to do the step 2. The step 2 is to work out the coordinate, right? As I said here, to work out the coordinate, you can just close your eyes and do a bunch of inner product, right? But in this simple example, we don't even need to worry about inner product. By visual inspection, we already figured out the coordinate, right? For example, x1t, as I said, right, will be something times phi 1t plus 0 times phi 2t plus 0 times phi 3t, right? So we know that the coordinate would be something 0, 0, right? So what is that something? Since we know this level is square root 3 over t, this level is 1, right? So that something will be just the reverse of that, square root t over 3. Is that okay? So the coordinate of x1t will be square root t over 3, 0, 0. Similarly for the others. So you see that for this simple example, we don't even need to mechanically compute the projection. By visual inspection, we figure out the bases and the coordinate simultaneously. Is that okay? So now the picture will be like this. So first of all, we have figured out a space. In this case, in this example, the space is 3-dimensional. Okay? By visual inspection, we figure out the basic building blocks. The bases are given by these 3 guys. And then based on this coordinate system, the corresponding coordinates for x1t will be square root t over 3, 0, 0. The coordinate for x2t will be square root t over 3, square root t over 3, 0, so on and so forth. Okay? So this is called geometric domain description. The original 4 signals. If I describe this by time domain, I draw you the 4 waveform like this. That's called time domain description. Now, if I give you a geometric domain description, I have to first define the coordinate basis given by this. So these three bases define a space, the three-dimensional space, based on this coordinate system. Then I can talk about, okay, my first signal has a coordinate given by this, second signal has a coordinate given by this, so on and so forth. And I can draw this. These are the three coordinates, three bases, phi 1t, phi 2t, phi 3t, phi 2t and phi 3t, the three axes. And then this is the point for x1t. This is a point for x2t. This is a point for x3t, and this is a point for x4t. Is that okay? So now, this is the so-called geometric domain description of signals. Now I have two choices. First choice is to describe the four waveform like this. Second choice is I give you 4 points like this. And of course, I have to tell you the coordinate system by defining what is my first basis, second basis, and third basis. Is that okay? That is what we mean by geometric domain. So now, to summarize, similar to the frequency domain description, geometric domain description is also one-to-one correspondence. I have a time domain description. This is time domain. And I talk about waveforms, right? Here, under a certain coordinate system, so under a certain space defined by the span of certain bases. Okay? So this defines the coordinate system. Then I can have a geometric domain description. Is that okay? Now, if I give you a time domain, this is called geometric domain. If I give you a time domain waveform, how do you figure out the geometric domain coordinates? The formula to use is inner product. Right? Etc. Is that okay? So this is like the so-called transform equation. I have the waveform. If I want to figure out the coordinate, I use these equations, this inner product, which is doing projection. Okay? Now what about the reverse? If I give you the points, I want to figure out the waveform. From here to here, what equations do I use? If I give you the points of my signal is x1, x2, x3, how do I get back xt? Well, from definition, right? So what is this? Phi 1, phi 2, phi 3t are three types of Legos, right? If I say that my object, which is the signal, has the coordinate x1, x2, x3, what do I mean? That means my object is equal to x1 pieces of type 1 Lego plus x2 pieces of type 2 Lego plus x3 pieces of type 3 Lego. Is that okay? I just pick appropriate number of Legos, add them together, then I get back the waveform. Okay, so this is like the analysis equation in the language of Fourier transform. In a way, this is a generalization because, as I said, for Fourier transform, the basis is restricted to sinusoidal basis. But here, we can custom make our own basis. Is that okay? Concept-wise, it's the same as Fourier transform. Now, you may wonder, why do we want to do this? We leave this to later discussions, okay? But I'm just telling you how to do it. Is that okay? Now, similarly, when I say Fourier transform, I say that these are just two angles to look at the object called signals. Same here. When I introduce the geometric domain description, like this, it's just two angles to look at the same object called signals. Same conclusion. No matter which angle you look at that, the physical nature of the signal will not be changed. So likewise, energy. Now you can actually compute energy from time domain, but also from time domain. If I give you the waveform, how do you compute energy? Energy is given by this, right? Is that okay? Now, if I give you a geometric domain, I say that my signal has this coordinate. Then how do you compute the energy? Well, It's very easy. The energy is given by the self-inner product of xt. Why? Because by definition of inner product, the self-inner product is given by integration of this one times this one, right? If they are the same, that means it's the integration of this guy, right? What is this? This is nothing but just the time domain energy, right? And then what is this? This is nothing but the norm of x in a geometric domain, right? So that means time domain energy equals to the norm of the vector square. Can you see that? So that means geometrically, for example, I have my 4 signals in a geometric domain representation are given by these 4 points on this space, right? Which one has the highest energy? If I ask you which one, if I only give you this geometric domain description, which of these 4 signals, x1t, x2t, x3t, x4t, which one has the highest energy? Of course, x4, right? Because x4 has the largest distance from the origin, square. Not only I can tell which one is largest, I can even compute how much larger. How much larger? How much, what's the ratio of energy of x4 compared to x1? Well, it's a geometric problem, right? That is the ratio of the square of this length over this length, right? So it's square root 3, right? I mean, 3 times, because it's a square, 3 times higher energy. Which makes sense, right? Because if you look at the time domain, this guy has 3 times more energy than this guy, right? It's consistent. Is that okay? So now keep in mind, geometrically, if you represent signals using points on some space, the distance of the points from the origin square give you the energy. Okay? That means if a point is further away from the origin, that signal has higher energy. Okay? And of course, power is given by the energy divided by the symbol duration. That gives you the power. Okay? Any questions? Okay. Now, before I move on, this is how, before I move on to talk about digital communication, this is so much for representation of signals, right? So far we introduced 3 ways to represent signal. First one, intuitively simple, time domain description. But usually, it will, you do not have much insight in representing signal using time domain waveform. Second method, Fourier transform or frequency domain description. So instead of talking about the waveform, we talk about the basic building blocks using sinusoidal basic building blocks. We talk about these sinusoidal basic building blocks behind the waveform. That's frequency domain description. The third way we just talked about, geometric domain description, is similar to the frequency domain description. The only difference is we can custom make our Legos. So instead of forcing ourselves to use sinusoidal Legos, we can design our custom-made Legos, so-called bases. And then we try to represent each of these signals as a different weighted combination of these Legos. Okay, so that's the geometric domain description. Is that okay? Now, in this example, it's so simple that I'm just using visual inspection to figure out the basis, right? You may ask, what if the 4 waveforms I want to represent are not that simple, right? You may not always be able to rely on visual inspection to do this, right? Then what would be, is there any systematic way to figure out the basis? The answer is yes, okay? And in fact, you have learned about this before in your undergraduate without probably realizing that. So let me spare maybe 10 minutes to talk about the stuff you should have already known after the break. So let's have a 15 minutes break, and then we come back to talk about that systematic procedure before we move on, okay?
上班上了一段脱房子，然后我不想上班了，那你就读书了。那我就开始考研。对呀、我们不是做那个，我们做了类似收费五次。是高级的，我说实话，是钱给的还是就是对于打螺丝这工作薪水来说给的，但是不要去比亚迪，不要那么差的。我就去这边就已经知道会很惨了，跟你说这么惨，会不是多少钱？对啊，就是你去的时候你都不知道什么状态。然后他那个领导又把这些看穿的声音，他们更看出来领导，我看你说你就是白跟你讲，你早跟我说嘛，我跟你这个人很差。对啊，他要求就把我，但是我心里他的领导都是大领导，所以他们他们其实就是百姓的领导，然后就这种不要提是上班过上班。拿到 offer 一个目标不用那么事儿，那之前我会觉得，我想出去玩，我把我手干了，玩一个月，玩了一个月的过程中，我拿到了要求，就是不然我们找工作，其实我们可以看好东西。其实我们也。哦，那个。因为我去年在追星，我需要钱，所以我去上这个班。但是我追了1年星，就上了1年班，等班上完了，我单也已经开了，最终是他完美突破完了我先钱。月底打球，我跑步也脱粉了，我不需要这个班了，我不需要钱了。这不需要钱了。原来就是感觉这个班虽然痛苦，这种后面越追这些的收视频，我就看着吧。然后后来我脱粉了，OK， 干了。现在想想，我还是来还钱。我追的时候其实也挺痛苦，就是因为第一次去线下看俩太好了，导致我后面一直念念不忘，结果发现当时一个新人物，后来就变成班子。这种我追过的经历。
Testing. Okay, this is optional, so it's just for your information. So as I said, what you need to do is, what you need or what is required in this course is just you have a conceptual understanding of this, okay? That would be good enough. I won't test you on very strange waveform and ask you to find the basis, okay? If I have to test you on this, I would, things will be easily obtained by visual inspection, okay? So, but then what I'm going to tell you is just for completeness. What if there is some strange waveform that you cannot find the basis easily by visual inspection? So in fact, as I said, there is a systematic method to do it. To do it. Now to introduce a systematic method, again, do a little bit of revision on what you have studied in undergraduate in linear algebra. This is something you have learned before, but probably without realizing that. So in vectors, right? So you should have learned this GSO procedure before. Have you? Do you remember this? Okay. So now some of you nod your head, but some is still full of question mark in your facial expression. So let's see. So in vectors, right, the GSO problem is like this. You are given a set of M vectors. Okay. So through the GSO procedure, you want to construct a set of bases, a set of orthonormal bases, which in general has the D orthonormal basis. So it will span a D-dimensional space, so that the space spanned, so that mathematically any of this signal, any of this vector in the original set that I want to represent would belong to the space spanned by this D orthonormal basis for all M. Okay, so that's the mathematical statement. In human language, it's saying that I want to represent these M vectors, right? But I don't have a coordinate system yet. Through this GSO procedure, I would gradually establish an orthonormal coordinate system that will be big enough to contain these original vectors that I want to represent. Is that okay? That's the GSO procedure. Now, how should I do it? Well, it's an iterative process, right? So first, I have no basis at all. So I need to first construct one basis, one axis first, so that with this one axis, I can construct a one-dimensional space, right? So what I do is I take one of these x1. Let's say I use consecutive orders. I take x1 first. Okay, and then I think about how should I construct a space that is big enough to just contain x1. What would be an obvious choice? So I need to find a basis for the one-dimensional space. That is one basis. So how should I construct this basis so that it will span a one-dimensional space that will contain x1? Very easy, right? So geometrically, if this is x1, so what should be my one-dimensional space? It would be my one-dimensional space, right? So then, in this one-dimensional space, what's the orthonormal basis? I just need to create a unit vector parallel to x1. That would do the job, right? So my first basis will be designed to be parallel to x1, right? So it's x1, but then I need to make sure that they are orthonormal, right? So the length is equal to 1, right? So I need some normalization. So obvious normalization is normalized with the length of this vector, so that this becomes a unit vector. Is that okay? So after step 1, I have constructed one basis, right? And then this basis define a one-dimensional space geometrically like this. Okay? So this space, this subspace will be big enough to contain x1 only, right? But my goal is to have a space that can contain all this xm, right? So then in the second step, so now I have a one-dimensional space. In the second step, I consider x2. Okay? So let's say, in general, x2 may be like this, right? So what does that mean? Geometrically, that means part of x2 will be contained in this one-dimensional space that I've constructed, right? But there is another part of x2 which is completely outside the space I have constructed, right? So, and I just need to construct the second basis along the component that are completely outside the existing space, right? I don't need to worry about the component of X2 that are already well represented by the one-dimensional space, right? Okay? So in this way, I can decompose X2 into two components. One is parallel to this existing space, right? The other is orthogonal to this existing space, right? So if I call this X2 orthogonal, I call this X2 parallel, okay? Then how do I construct my second basis? I want the second basis to be orthonormal, right? So therefore, I will choose my second basis to be parallel to this component, right? Because by this construction, I will have an orthogonal basis, right? And also, phi 1 and phi 2 together will construct a two-dimensional space that can contain x1 and x2 together. Can we see that? Okay? So the natural choice will be I take this component, orthogonal component, and I normalize with this orthogonal component. That would be my second basis, right? And by construction, this second basis and this first basis will be orthogonal. And each of them have unit norm. Is that okay? Now, of course, I still need to figure out what is this orthogonal component, right? So if I write x2 equals to this x2 orthogonal plus x2 parallel, right? So how do I compute x2 parallel? What is x2 parallel? It's a projection of x2 along this basis, right? How do we compute projection? Algebraically. Inner product, right? As I mentioned. So this x2 parallel, this guy, is equal to what? Projection of x2 along the first basis, right? And this is parallel to the first basis, right? So this is this component. Can you see that? This is the projector length multiplied with the unit vector. This gives me the projector vector. Okay? So I have x2. x2 is given. I know this, right? So this guy would be simply given by x2 minus x2 phi 1 times phi 1. Is that okay? So this is something we can compute entirely from x2. So using this, substitute into here and here. Then I get my second basis. Is that okay? Now at this point, we have constructed a two-dimensional space, right? What can we say about this two-dimensional space we have constructed? This two-dimensional space will be big enough to contain x1 and x2. Is that okay? So now, but this is not yet big enough to contain all these m guys, right? So we continue on to step 3. On step 3, let's say we take x3. Okay? If x3 is also on this plane, let's say x3 is, I don't know, here. Then we ask, can this existing subspace contain x3 as well? Yes, right? Then x3 is fine. Then we move on to talk about x4. Okay? Now, if, let's say, in general, x3 is not like this. Let's say x3 is like this. Then that means there are part of x3 that can be well represented within the existing two-dimensional space, which is this whiteboard. But there is also a component of x3 that is outside this whiteboard. So this would be the component, right? So then we just form the third basis by a normalized version of this orthogonal component. Is that okay? Then how do we compute this orthogonal component? Using the same idea. We decompose x3 into a component which is on this existing two-dimensional space, and then the other component is an orthogonal component. And then we just form the third basis from this orthogonal component. Is that okay? So step by step, iteratively. In the worst case, let's say each time I take a new xi, I will need to form a new basis. In that case, in the worst case, how many bases do I need? What can we say about the dimension? In the worst case, it will be equal to the number of vectors I want to represent, right? But this is only the worst case. as I said, sometimes it may be x3 is also on this plane, right? If that's the case, then my dimension, overall dimension will be n minus 1, right? If x4 is also on this space, then my dimension will be n minus 2, right? So in general, what we can say is the dimension of the space needed to completely represent this m given vectors will be less than or equal to m. Is that okay? So, and then at the end, what we produce by this GSO procedure is orthonormal basis with a dimension d less than or equal to m. Is that okay? That's the GSO procedure you have learned before. Do you remember from your linear algebra? Okay? So now we are doing exactly the same. Let me use this. Then now the GSO procedure for our step 1 is just like this. We have m signals that we want to represent, right? So we want to use the same GSO procedure to get the d basis of a normal basis so that it will span a space big enough to contain these m signals we want to represent. You think about these two things, are they the same? It's the same, right? The only difference is in the past, you're doing vectors. Now, we specialize the vectors into signals. The others is the same, right? So look at step 1. So in step 1, let me write it here. The first basis will be formed by what? We want to pick x1t first, right? So we want to form the first basis parallel to x1, but a normalized version. So what we want to do is x1t, but normalized with the norm of x1t. Is that okay? What is the norm? Self-inner product square root. Is that okay? We know how to compute inner product for signal, right? As we just talked about before the break. That is, after step 1, I got a one-dimensional space. This one-dimensional space would be big enough to contain x1t only. Is that okay? Now, with step 2, it's the same idea. With step 2, I take x2t. So x1t may be here. So I form a first basis parallel to x1t, right? And my x2t may be here, right? So then, using the same logic, I just need to form the second basis by designing that to be parallel to the orthogonal component of x2t, normalized by its norm. Is that okay? It's the same formula. The only difference is, how do we compute this component? In the past, in the vector, it's given by this, right? Here is exactly the same formula, except that for signals, you need to modify this inner product with the integration. Everything else to be the same. Is that okay? So if you understand this, you should understand this. So on and so forth, right? So that's why, that's why I told you, this is something you have already learned before, without probably realizing that. Is that okay? So therefore, the dimension of the space required really depends on the specific features of these m given signals. Okay? The worst, what we can only say is, in general, I need a m-dimensional space in the worst case. Okay? The second observation, again from this GSO procedure, is the bases obtained, are they unique? Are they unique? They are not unique. Why not? Now look at this procedure. How do you form the first basis? You form it by setting it parallel to x1, right? Then how do you form the second basis? You set it by parallel to the orthogonal component of x2, right? So on and so forth. What if you swap the order? Instead of natural order, let's say you do the reverse order. You can also work out the same procedure by taking the first basis to be parallel to xm, right? That logic will still work, right? But then if you do it this way, the basis you obtain is obviously different from the natural order basis. Is that okay? So in general, you can have a different permutation You can have m factorial permutation. Each permutation will give you a different set of bases. So basis is not unique. And this shouldn't be surprising to you, because suppose the space I'm talking about is this whiteboard. To span this whiteboard, I can have different bases, right? I can have a basis like this, right? This orthonormal basis can span this whiteboard, right? I can also have a basis like this. This second set of bases will also span the same whiteboard, span the same space, right? So the space behind this basis is the same, is unique, but the basis, specific choice of basis, is never unique. Is that okay? So just keep this in mind. So for example, in this toy example, by visual inspection, these are the three bases, but they are not the only choice of bases. You can also have some other weird choices of bases, okay? What we can say is, no matter how you choose it, you need three-dimensional space. You need three orthonormal bases to do your job, okay? Okay, so that's the GSO procedure. Once again, I won't test you on very complicated waveform and ask you to do the geometric domain conversion. That means I won't test you on this GSO procedure. You don't need to know it. But since I guess many of you have learned it already, so I just thought that maybe just a remark will help you to connect with what you have learned before. Okay? Any questions? Okay? If no, then that's it. Okay? We talk about three ways to represent signals, right? And then we go back to, we show our journey about communications. Okay? Remember, communication is the what? Deliver of information from one point to other point, right? That's communication. So now let's look at communication perspective. So in a digital communication, you will have a transmitter, and then you have a receiver, right? And in between, you have something called channel. I guess last time we talked about an example of channel, coaxial cable, right? When we talk about long-distance telephone communication. So in general, for a digital communication system, we will have at least these three components. So a first order question to ask is, as an engineer, do we have the freedom to design the transmitter? Do we have the freedom to design a transmitter for a communication system? Of course, yes, right? In this course, in the first part of this review, I'm going to cover how should we design the transmitter and receiver as well, right? So as an engineer, we can design the transmitter, we can also design the receiver, right? Okay, for those of you with EE background, you may have learned about different modulation method, BPSK, QPSK. These are examples of different design of digital modulator and the associated demodulator. So of course, we have the freedom to design transmission schemes and reception schemes, right? No question about this. Do we have the freedom to design a channel? Do we have the freedom as an engineer to design the channel? No. Usually, a channel is just a model, a faithful model to represent the physical degradations of signals. For example, this can be a coaxial cable. With a coaxial cable, as we explained last time, you will introduce attenuation and then you have noise, right? So if you have to build a model for the coaxial cable, it will be basically an attenuation plus noise, okay? It's just a faithful modeling of the physical process. If this is a wireless channel, then you will have a corresponding model for wireless channels, radio channel. Well, even if you're talking about radio channel, but with a different carrier frequency, you need very different models as well. If you build a radio channel model for 900 megahertz carrier frequency versus for 28 gigahertz carrier frequency, the two models will be very different. Is that okay? So usually, we don't have the freedom to design the channel. So this is maybe a good news or bad news, depends on how you look at that. There is no such thing as a universally optimal transmitter and receiver design that can work for all channels. Let me repeat. There is no such thing as one size fits all. If you design the transmitter and receiver that works for one type of channel, the same design will likely not work for other types of channel. Is that okay? Now, I said this may be a good news or bad news, depends on how you look at that. For example, if you're a lazy person, that may be a bad news. That means you spend all the effort to design a transmitter and receiver that works well for one type of channel. But now, if you have a different channel, different situation, you may need to redo the design again. Okay, so that's bad, right? From that laziness perspective. But it's also a good news, especially if you are very interested into the communication designer. That is the reason why a communication system engineer with 10 years of experience worth higher salary than a junior engineer. Okay, because for different situations, you need to exercise your experience and understanding to design with an optimized system for a particular channel. Okay, so because of this, if you are given a certain situation, the very first thing you should do is not to design the transmitter and receiver. What's the first thing you should do? The very first thing you should do is, if there were no model for the particular situation, the very first thing you should do is to build channel model. Or at least understand the channel model. Understand what are the specific degradations introduced to your signal before you should go ahead and design the transmitter and receiver. So that's why if you look at the literature for example, cellular network, in the 70s and 60s, the very first bunch of papers is not about design transmitter receiver. The very first few papers are actually talking about channel modeling, measuring the attenuation, path loss, whatever, properties. Those are based on empirical measurement for 900 megahertz carrier radio channel. Okay, there are a bunch of very important papers at that time trying to do this kind of empirical channel modeling studies. So only after you have a sufficient understanding of the channel, then you can, only after that you can start talking about transmitter and receiver design. Is that okay? So let's keep in mind, one size does not fit all. Okay? So that's number one. Now, we will focus on digital communication. Now, what is a digital communication system? That means the input to the transmitter will be bit streams. You input a certain number of bits, a file, okay, to the transmitter. Let's say you send 1,000 bits to the transmitter. The receiver will give you the same number of bits as the output. If you send in 1,000 bits, the receiver will give you 1,000 output bits. Is that okay? That would be a digital communication system. Now, let me ask you, given that this is a digital communication system, what can you say about the signal here? Are they analog or digital? Do you understand what I mean? At the output of the transmitter for a digital communication system, for a digital transmitter, the output signal here, is it analog or is it digital? Analog, okay? Strictly speaking, the signal, whatever is the transmitter, the signal here should match the requirement of this channel. Okay, so if this is a coaxial cable, by nature, the input to the coaxial cable would expect an analog waveform. So you should generate an analog waveform that match the requirement of the channel. So if this is a coaxial cable, as we talked about last time, this will be an analog baseband signal. Okay? If this is a radio channel, this should be an analog bandpass signal. Okay? You know what is the baseband, difference between baseband signal and bandpass signal, right? I guess. So in other words, this one, since most of the physical channels are analog channels, so you will expect most of the time the input and output to the channels are analog signals, despite the whole thing is a digital system, digital communication system. Is that okay? Digital only refers to this input interface and output interface. Just keep this in mind. Okay, so with this introduction, so let's look at how should we, so now we have a digital communication system. So how should we define performance? We want to assign some metric that can quantify the performance, right? So as a user, as an end user for a digital communication link, what would be the important metric that can quantify the performance? So what kind of performance you will be concerned as a user? Think about you are trying to subscribe to internet service provider A or internet service provider B. They give you different prices, they give you different packages, right? So how would you decide? You want to pick the one that is having better performance, for example. So what kind of metric you will look for? Bit rate, right? So if you have to send 1,000 bits, you are concerned about how long it takes you to send a file, right? So bit rate, what is bit rate? What is the definition of bit rate? You time for 1 second, and you count how many bits are transmitted to the other side, right? So number of bits per second. So units is bits per second. Is that okay? So the higher the bit rate is, the better the performance, right, for a digital communication link. That's understood, right? What else beside bit rate would you concern regarding performance? So let's say you have a very high bit rate. Would that be you are satisfied with that? You also thank you. You also should concern about the reliability, right? Right. So let's say this communication link can send 1,000 bits very fast, but these output bits are all corrupted, right? That's not very good performance, right? So you're concerned about reliability. So reliability is quantified by, for example, bit error rate. What is bit error rate? It's just a ratio. The denominator is the total number of bits you transmit. The numerator is the number of bits corrupted. Right? So let's say I send 1,000 bits. At the end, the receiver receives 1,000 bits. But out of this 1,000 bits, 100 bits is corrupted. Then the bit error rate is 100 over 1,000. Is that okay? So it's like probability, right? Probability of error. Now, this is the number, of course, between 0 and 1, right? What is the best case bit error rate you can expect? What's the best bit error rate? 0, right? 0 means you have no error. That's, of course, very good, right? What about the worst case bit error rate? 1, right? Agree? 0.5. Okay. Now, numerically, of course, the largest bit error rate is 1. But imagine if the bit error rate is 1 for this communication system. What do we mean? I send you 1,000 bits, and I guarantee all these 1,000 bits will be incorrect. And what can you do? You just flip the bits you will receive, right? So in other words, bit error rate of 0 is as good as bit error rate of 1. Can you see that? In both cases, you have no uncertainty, right? Then what's the worst case bit error rate? 0.5. Because with 0.5, you have the maximum uncertainty. Why? Because you can easily imagine. Normally, with a receiver, you should be able to do better than coin flipping, right? So because you are able to get a noisy observation of what could have been transmitted before you make a decision, right? So, but if your communication system has a bit error rate of 0.5, this is the same as you forget about, you ignore what you observe, and you locally flip a coin to determine the output bits, right? And we know coin flipping have a bit error rate of 0.5. So if your design communication system have this bit error rate, then that is obviously the worst case bit error rate. Is that okay? All right. So these are the two performance metrics that people will be concerned, right? As a user, you want the digital communication system to give you a high bit rate, and at the same time, low error probability. Okay. Oh, by the way, speaking about bit rate, this reminds me of again a common confusion. So I have to tell you a story. So around 15 years ago, 2008, I guess you were all very young. It was the Beijing Olympic, right? You still remember the Beijing Olympic? Yeah. So at that time, there was a very popular guy, 110 meters record holder, Liu Xiang. You remember him? You heard of him, right? At least. So Liu Xiang was a very popular guy at that time in China. So in Hong Kong at that time, there were an internet service provider just leveraging on this Beijing Olympic. The company A making a commercial advertisement. The advertisement is filming this guy, Liu Xiang, running on the track, projecting an image that very fast. He runs very fast, right? So that projected message is the surface provided by this internet service provider is as fast as Liu Xiang. Is that okay? Just a superficial commercial advertisement. But then a week later, a competitor, company B, put up another advertisement. The message of the second advertisement is saying, no matter how fast you run, you cannot exceed the speed of light. And the second operator is using optical fiber. Okay? So that is basically, acting against the first company. But as a layman, it's funny, right? But as an engineer, what's wrong with the logic? You understand the logic of the second company? Also the first company. First company is saying, this guy runs very fast, so my surface is also as fast as him, okay? The second company is saying, no matter how fast you run, you cannot exceed the speed of light. And my surface is delivered using optical fiber. So signal travel at the speed of light. What's wrong with this logic? The problem is, I guess this is also due to the use of this adjective. When we describe a bit rate, we use the adjective fast or slow, right? So this fast or slow is overloaded with another meaning, how fast signal travel, okay? In fact, we will see very shortly, bit rate, how many bits you can deliver to the other side, has nothing to do with how fast signal travel. Can you see that? Be it be traveling at the speed of light or half of the speed of light, it doesn't affect the bit rate. Okay? So how fast signal travel on a channel affects what? Delay, propagation delay. If I send the first bit at t equal to 0, how long it takes you to receive the first bit? That depends on how fast signal travel, but not the bit rate. Is that okay? So both of this commercial advertisement is totally wrong, technically. But anyway, so this is just to show you, to tell you a story that laymen sometimes may be confused between bit rate and how fast signal travel. Anyway, so these are the two important performance metrics that measure how good the digital communication system is delivering to the user. Is that okay? Besides performance, we also have a resource metric. Okay? Now, the resource depends on money at the end. Okay? And of course, the translation from resource to money depends on a specific type of channels, right? If this is a coaxial cable, you will have a specific resource metric. Now we are focusing on wireless channel, radio channel for now, okay? So for radio channel, what are the important resource metric? For radio channel, you know that the radio spectrum is regulated globally. That means it is illegal. In fact, it's criminal if you transmit something on the air without a license. So before you transmit anything on the radio spectrum, you need to have a license. Otherwise, it's criminal. Is that okay? So a license is usually very expensive. Okay, we will talk about this in more detail later. So, but a license is actually very expensive. Behind the radio spectrum license, there are three important parameters. First one is the carrier frequency. Second one is the bandwidth. Third one is the power mass. Okay, the power mass determines how much power you can transmit. So the first effective metric is the bandwidth. Okay, if your communication system demands a higher bandwidth, then you need to get a license with a larger window of frequency, and which is going to be more expensive, because as we know, it's just like land. Spectrum resources are regulated, and they are usually heavily congested. Okay, the supply of good spectrum are very limited. So if you demand a larger piece of spectrum bandwidth, then it's going to be more expensive, right? Okay, so bandwidth is one. The second resource metric is power. And obviously, if you demand higher power, you're going to have higher costs eventually. The detailed translation of this resource metric into the money cost depends on the situation, which we will elaborate later on. Okay, so for the resource metric, we also have two important metrics behind the radio channel. And for the performance metric for digital communication, we also have two metrics quantifying the performance. So in general, we know that if we want to improve the performance, if I want to improve the performance, I need to invest in more resource, right? Now, to be more precise, what do we mean by improving the performance? Do I mean increasing the bit rate? Or do I mean decreasing the bit error rate? These are two different things, right? When I say I need to invest in more resource, what do I mean? I can mean increasing the bandwidth, or I can mean increasing the power. These are, again, two different things. So altogether, there are four possible mechanisms of the trade-off between performance and resource. So, for example, I can mean increasing the bandwidth leading to increase in bit rate, okay? Or I can mean increasing the bandwidth leading to reduction in error probability. So these are two different mechanisms. Similarly, I can mean increasing the power, bringing a reduction of error probability. Or I can mean increase in power, bringing an increase in bit rate. Again, these are two different mechanisms. Okay? So now, in the revision, I'm going to cover the digital modulation theory and demodulation theory. And based on this, I'm going to explain this big picture, the four trade-off mechanism. Okay? So this will be a summary of those of you who have studied or who claim to have studied communication theory. If you have studied communication theory well, you should be able to explain or comprehend these four trade-off mechanisms. Okay? If you cannot, that means you still have gaps in the understanding of communication theory. Okay, so that is what we're going to cover. Now, of course, as I said, right, the design of transmitter and receiver depends heavily on the particular type of channel. To make your life easier, at least in the initial review, we will consider just a very simple channel. The channel is just what we call additive wave Gaussian noise channel. So your received signal here at the output of the channel is equal to your transmitted signal added with noise. Okay? So the channel will do nothing to your transmitted signal except adding noise. The channel only adds noise to contaminate the signal you transmit. Okay? So this is like a simple case. This simple case is also not, sometimes it's quite realistic. For example, for satellite communication, where you have a line of sight propagation. So for this kind of channels, it's pretty much additive wave Gaussian noise. Okay? So we will look at this additive wave Gaussian noise first, and how we design the transmitter and receiver to overcome the effect of noise. All right? So, well, okay, I don't think I have time to talk about the communication transmitter now. So I will stop at this point, and then I will talk about the transmitter and receiver design next time, okay? With the aim of explaining this four trade-off mechanism. All right, so I'll see you next time.